Okay, so let's begin. Can we go to the...
Can I share my screen?
Yes.
Can you see it?
Not yet.
Okay.
Yes, now it comes.
Okay.
Maybe it try. Yeah. Okay. So welcome everybody to the second talk of the day. We are delighted to have Professor Saurya Das from Lethbridge, Canada, and he's going to talk about singularity-free classical theory of gravity. Maybe I can send you a reminder when 5 minutes are left.
Sure. Maybe even 7 minutes before then.
Okay, sure.
And it's a 45 minute, right? In all, including questions.
So 40 minutes talk, and then we have some time for
A few minutes.
questions.
Okay. So 45 minutes. Okay. So can I start?
Yes, please.
Okay. Thank you firstly for, you and the organizers for inviting me. It's greatly appreciated. Oops. Sorry about that. You can hear me, right? Clear? Loud and clear?
Yes.
Okay, great. Thank you. Yeah, thank you very much. It's kind of a bit early in Canada now, so I've missed part of the very interesting talk by the previous lecturer. Sorry about that. Yeah, it's my great pleasure to be here. I'll begin. Again, my name is Saurya Das. I'm from the University of Lethbridge. It's in Western Canada, in the province of Alberta. So the rough outline of the talk is I would briefly remind or try to review why we need to, or what's the compelling or not reason to try to quantize gravity. We'll talk a little bit about singularities in gravity, Newtonian versus relativistic, and then I talk about some singularity-free potentials as vacuum solutions, and there are roughly two kinds or classes. Then I'll do the Newtonian theory, just because we start with the Newtonian theory, but of course we have to do a relativistic theory, which I will do. And then I will talk a little bit about the implications of quantum gravity in cosmology. That's the paper downstairs, you can see, and another one is in progress. So why do we need to quantize gravity in the first place? Or what's the motivation behind it? Let's look at a little bit about other theories which we understand better. For example, for the Yang-Mills theory, we know that phenomenologically there are things which quantum mechanics cannot explain, and there are some of them are listed there. So it's compelling that you have to do a quantum field theory version of that. Now, in gravity, that's kind of lacking, because although we have phenomenological quantum gravity phenomenology and all that kind of things, however, something is happening with my mouse. Sorry about that. I'll try to be more careful. But there are no really compelling, to the best of my knowledge, experiments which say that you have to quantize gravity to explain this, right? So there's a question mark. So that motivation clearly not as compelling as, say, Yang-Mills theory. There's the other aspect, which is singularities, which in Yang-Mills theory, for example, or gauge theories, we know that there are Coulomb singularities, and self-energies become infinite. And these are things which quantum field theory or quantum version of say, QED or QCD can handle. In gravity, we have singularities as well in terms of curvature scalars blowing up and geodesic incompleteness. That, to me, is a greater or at least equal motivation for to make a case about quantization of gravity, because you cannot have singularities in a good physical theory. If you have singularities, then basically the theory on Einstein's gravity fails, right? So right. So what do we mean by singularities? Let's just say, let's talk about singularities in gravity in particular. So if you have, so let's talk Newtonian first. There are at least two ways of seeing it. For example, if you had a point particle, right, of let's say mass m and radius rho, then the Newtonian potential, as we know, blows up as r goes to 0, and the self-energy of such a sphere also, as you can see, it goes as 1 over rho, which the radius also goes to infinity as rho goes to 0. So this is one of the easy ways of showing that, as we know, that Newtonian, from Newtonian perspective, you have a singularity. Relativistic too, there are, one of the simplest ways of seeing is, let's say, for the Schwarzschild black hole or for any black hole or even cosmology, at the singularity at r equals 0, the Kretschmann scalar blows up as 1 over r power 6. It's a really bad singularity. However, we also know that the Kretschmann scalar, the curvature scalar going out, is often a good indication of a singularity. However, it's neither necessary nor sufficient for singularities to be present. Yeah, and the main tool for singularity or diagnosing a singularity is the Raychaudhuri equation and the Hawking-Penrose singularity theorems, and I will go a little bit about it. Now, it's like a two or three slide quick review of the Raychaudhuri equation and singularity theorems. So basically, what happens is that one can show, and I'll go to the next slide, that unlike any other physical theories that we know of, the trajectories, or the geodesics in this case, it can be shown quite rigorously that for most physical spacetimes, the geodesics end at some point. And end meaning like, there's a pathology there, because normally trajectories never end. Even if I sit tight here, my world line would go from -2 plus infinity, right? So unless it hits its singularity. So that's the basic idea. And again, there's probably the likely experts in the audience, so I wouldn't go into too much of details, but I'll be happy to answer any questions. Essentially, you have a congruence of geodesics, which means a set of near pencil of geodesics. And if you write the velocity field, which is this u, is the field of velocity defined at every point. And then if you take the total derivative, you do a little bit of differential geometry, a little bit of algebra, and then if you take the trace of this equation, you end up in this so-called, as we know, Raychaudhuri equation. And as you can see, most of the terms on the right hand side are negative, okay? And from this you can show that for geodesics, they will converge, they will form this cusp in a finite proper time. That's the main result, or the primary result, of the Raychaudhuri equation, which is actually the engine behind the main ingredient behind the Hawking-Penrose singularity theorems, right? And the way it works is that if you look at this, let's say this is a Riemannian manifold as opposed to pseudo-Riemannian, S2, just the surface of the sphere or the Earth. If you take a great circle, right, between any 2 points, the shortest distance is normally we call a great circle, but there's another geodesic, if you like, which goes the other way around between any 2 points on the surface of the Earth, and that longer curve which joins the 2 points, which is also a greater circle if you like, has 2 conjugate points, the 2 poles, right, where the geodesics converge. So in Riemannian manifold, the consequence of having conjugate points is that the curve, the great circle, the geodesic joining them, is no longer a minimal length curve, it's a maximum. For pseudo-Riemannian, you can show again without going into too much of the differential geometric details, but the result is in a pseudo-Riemannian manifold is the other way around. If you have conjugate points, which the Raychaudhuri equation predicts, the geodesics are no longer maximal length curves, they are minimal length, they're not maximal length curves. However, maximal geodesics are predicted by global arguments, as we know from the other hand, right? So therefore, on the one hand, you see that maximal geodesics should exist. On the other hand, the Raychaudhuri equation via its conjugate point shows that geodesics is no longer maximal. So there is a contradiction, apparent tension between the two. And the only resolution of this tension, of this this problem, is the conclusion that sufficiently long geodesics cannot exist and geodesics are incomplete. So this is mainly the consequence of the implication of the singularity theorems. But again, the blowing up of the curvature scalar is definitely often a strong indication of a singularity. So we'll go by both. So first, as we said, we will try to deal with this in a Newtonian setting just because it's easier to understand and it gives a good intuition, but of course everything has to be relativistic in the end. So if we are talking about a non-singular Newtonian kind of potential, let's see what the required properties are. So you look at this picture on top, it's a mass m, and I've plotted the various length scales in the gravitational problems and a logarithmic or some such, it's certainly not to scale. And you can see that let's say the Newtonian version of gravity, or its extension, the relativist version as well, often the Newtonian suffices, as we know, has been verified roughly up to the cosmological scale on the large side. In the smaller side, it's only verified to about, this is like last year's data or something like that, 10 power minus 4 meters, about 10th of a millimeter. Okay, so underneath this, it's anybody's guess. So the Newtonian potential 1 over r or 1 over r squared in terms of field has not, nobody knows whether it holds good to below these length scales. So what we postulate at this point is that the potential goes to, instead of infinity, it goes to a constant at r equals 0, and a certain number of derivatives are also goes to 0, because we know that essentially the second derivative of the potential is the curvature. We want that to go to 0 as well. And the number of derivatives going to 0 determines in the end like the order of the differential equation of the law that we're talking about. Okay, so this is the bare minimum conditions that we impose. Now let's go to the next slide. Now, if we impose this condition, we immediately see that one of the problems that, well, the problem of the self-energy goes away right away, because the self-energy of a sphere right now is this potential, let's say, of a point particle. If a self-energy of a point particle, such as the gravitational self-energy of an electron, is infinite, as we know, because r equals 0. But in this case, as you can see clearly here, that since the potential is finite at r equals 0, the self-energy is finite as well. And later we will see that if we transcribe this into a relativistic language, the Kretschmann and curvature scalars will be finite as well. So, so first, again, as I said, let's continue with the Newtonian theory. And what is a Newtonian theory? The field equation for a Newtonian theory is the Poisson equation, right? It's the Poisson equation in gravitational physics, and it's the Poisson equation which needs to get changed. So how do we, at least formally, arrive at a modified Poisson equation which would encompass this non-singular potential. So let's consider potential V of r, spherically symmetric. Now, formally, the Poisson equation for any potential, any theory of gravity, can be written as in this, as you can see in this red here. So the right hand side is the density. Essentially, this is the potential. V tilde is the Fourier transform of this potential. And if you do the Fourier transform, you take its inverse, and instead of k, you essentially replace minus I gradient. And so this is a differential operator. Essentially, this is the Poisson equation. For example, if the potential is of this form, it's a non-singular potential. I've added this kind of Ikawa tail to it just to make it more regular. And if you do the Fourier transform and all that thing, this equation here. It's a kind of unwieldy looking, but it's what it is. This is essentially the Poisson equation that you have. It's complicated, but formally it exists. For example, for lambda equals 0 here and p equals -1, which is Newtonian, immediately from here you get back the standard Poisson equation. But formally, again, it could be non-local and all that, but this is the formal Poisson equation for any potential, including non-singular potentials that we have in a Newtonian theory of gravity. Any quick questions or clarifications up to this point? Okay.
It seems not
Go ahead.
from the audience. You can go ahead.
Okay.
No,
go ahead, please.
Yeah. No, I'm saying there are no questions from the audience. I can see.
Okay, fine. And yeah, thank you. And if there are at any point, feel free to interrupt me. Not a problem. Right. So then we go to the next slide. So we want a potential which is non-singular at the horizon. So roughly speaking, we can classify into two kinds of classes. One is when the potential is an analytic function, where you can do indeed a Taylor expansion, as we know, near r equals 0. And another case which we studied as well, which is when it's not an analytic function. So when it's an analytic function, for example, this is like the one you have here, v, a few points here. So this is an analytic function, as you can see. This is a potential which fits the bill in the sense that this gives rise to what we want, in the sense that at long distance this is Newtonian. You can clearly just check it out. And in short distance, you can see it's a non-singular potential, right? So this potential, and I'll draw some graphs and things like that, is a class, is a large class, I would say, of non-singular potentials which go over, boil down to Newtonian at large distance, as it should, because it's over a millimeter or something. It's been verified to be true. And inevitably, when you do such a thing, a length scale L sort of automatically enters the problem. You cannot do it without the length scale. Now, physics-wise, that's not that's kind of understandable, because that's the length scale. The significance of the length scale is that that's where the potential or the field changes from Newtonian to what we know Newtonian to something which is non-Newtonian. And just to give an idea, so this length scale doesn't have to exist. And if you just look at gravitational fields or gravitational interaction, gravitational experiments, then this length scale again could be as large as 10 power minus 4 millimeter. And it can go as small as Planck, because, well, below Planck length, we really don't know what we're talking about. So it could be as large as this, or if we include standard model interactions in this picture, so not just gravity, but let's say we formulate an interacting field picture with this kind of theory, then the length scale could be as small as the electroweak scale, because no deviations of anything coupled to standard model excuse me, has been observed till the electroweak scale or the Large Hadron Collider scale, right? So, but my point is that this scale could be quite large as well, just from the experimental point of view. Similarly, if we take a look at the analytic function, it's pretty simple. It's looking like that, and it's Newtonian short distances. There could be a non-analytic class as well, which is, as you can see, it's e power minus L over r, and r goes to 0. I mean, it and all its derivatives go to 0. Therefore, it's a non-analytic function. But who knows what nature chooses? Therefore, we considered this case as well. This too, it's large distances. It is Newtonian. One of my a postdoc of mine is working more on this particular potential. But anyway, such a potential can exist as well. Now, if you look at the graphs, so the green is the Newtonian potential. It's minus 1 over r, as you can see. The blue is the analytical potential for a certain value of n. And to remind ourselves, this n is this number here. Okay, we can assume it to be a positive integer greater than, be a positive integer without loss of generality. And the brown is the non-analytic potential, which is this example there. Okay, and obviously, as you can see, for large, well, few things. For large r, they all, boil down to, they all coincide with the Newtonian as it must. It's only at short distances that there are deviations, and this deviation kind of happens around here, okay, around this part here, if you can see my cursor, and this is essentially the length scale that one is talking about. All right. So, and as you can clearly see, whether it's whichever form of potential we take, which can replace the Newtonian potential near r equals 0, they're actually finite, as opposed to the green, which becomes negative infinity. Okay, so it kind of does the job. If you look at the field of the potential, which is essentially the negative derivative, as you can see here, this is interesting, because again, the green is the Newtonian one. Now, in this case, both the blue and the brown are both the analytic, just because it's easier to work with the analytic. And although, as I said, we don't know what, if any, or what if any, nature chooses. But whatever, it kind of exemplifies what we would like to say. So they are both the analytic forms of the potential. So let me show it once again, remind ourselves here. So it's this form, one in red, for two values of n, one for small n and one for large n. And let's see how the graphs look like. So you can see that for large r, of course, it coincides with the Newtonian potential field, as it should be. For small r, there are deviations. So both the force fields for both n equals 8 and n equals 30, they go to 0, as it should, right? But here, as you can see, that from an attractive phase, it goes to a short repulsive phase, and then it goes to 0, okay? And the repulsive phase, or the height of the repulsion of the repulsive force, that's determined by this number n, and it's a feature of this model that the higher the n it is, the sharper this peak is, which means that for higher and higher n, the transition from the Newtonian, so from the Newtonian to the non-Newtonian, is sharper the higher that value of n is, okay? And in fact, for very, very large n, I mean, not infinity, let's say 100 or something like that, this peak is almost like a wall. So the transition from the Newtonian to non-Newtonian is really, really sharp. So that's the significance of the number. Any questions so far? Okay, I'll go to the next part then. So basically we have a Newtonian theory because we have a Poisson equation, we have a consistent potential, or set of our class of potentials, which is Newtonian for large distances and non-singular for short distances. That's the main result here. Now let's go to the relativistic version now, which is of course the motivation for all of this and for doing all of this. So how do we go? We go the simplest route, which is we identify the potential, we translate it into the language of the metric. Now, if there are any questions, please do ask, but keep in mind that for a non-singular case, we assume that and if it works, it works, if it doesn't, it doesn't. But we start with the assumption that there can exist a potential which is non-singular everywhere, and which is not very large everywhere, right? It goes to, as you can see here, that if you look at the potential, it's kind of the green one goes to very, very large negative values, but the other ones don't. So it's always close to flat space, if you like. And therefore, this identification of G naught naught, the metric which 1 plus 2v remains valid. And as many of you might have noticed, that there should be a 2v over c square. I didn't just put it because I put c equals 1, but in terms of units, it should be there. So why FR gravity? F of R gravity. And I assume most of the audience knows about it. It's a generalization of Einstein gravity, where the Lagrangian density R is replaced by some function of R. And the motivations are manifold. Well, yes, this is the simplest generalization of FR equals R, which is Einstein, right? So you generalize, you replace R by F of R. So it's arguably one of the simplest. It's connected, as can be shown, to many other modified theories of gravity, such as Brans-Dicke theory. So F of R is kind of a all-encompassing, it's a very generic, very general class of theories. So it's no wonder that we found it useful. And also one can show that if you write it in this language, often it's can be written as very similar to gauge theories. For example, if FR is R squared, it's similar to F equals F squared or trace F squared in Young's theory. So that's there. And again, as I'm sure many of you know, that F of gravity theories is quite important or quite useful, as has been seen in cosmology. So these are our motivations. And as I said, our primary motivation is that it encompasses many modified theories of gravity one way or another. Okay, so I'll have 2 or 3 slides with, oops, sorry. I'm having a little bit of issue like this zoom bar, right? And that's kind of obscuring some of the type. Anyway, so this is again a lightning 2 or 3 slides on FR gravity. So the Lagrangian and the action is of this form, where F of R is not R in general. This is a little bit of notation. The metric, we assume we are considering spherically symmetric systems. So we assume the metric to be diagonal, and with these 2 unknown functions S and P, they're not like inverses of each other, because we are considering the most general form. I assume S to be 1 plus 2V, and I can write it as 1 plus delta S. And so we are always perturbating around flat space, okay? So 1 is for flat space, and 1 is for and in this case f of r equals is Einstein gravity. X is a product of S and P, which is also for flat space is 1, so it's 1 plus delta x. F of r is r, which is Einstein, plus delta f of r. And capital F, so there are two f's. Small f or lowercase f is the modification of the Lagrangian density. And capital F is simply the derivative of small f with respect to capital R. And again, for Einstein gravity, general relativity, we know it's 1. So we write everything in terms of deviations, okay? And then if we write the equations of motion, so I repeated the action here with now f of r written as r plus delta f of r. And Einstein equation now becomes, instead of capital G mu nu, which is the Einstein tensor, it becomes capital G mu nu plus a little bit of change. And that change in terms of fr gravity is exactly this. And if small f is capital R and capital F is 1, this goes to 0, you get the Einstein equation. Well, the twofold reasons for writing this, firstly to show that there, and again, as many of you perhaps know, that there is a precise formulation and you get a precise equation of motion. It's actually not as bad as it looks. If you actually work with it, especially for simpler systems, spherically symmetric systems, it's quite a simpler, boils down to simple differential equation. And secondly, the reason I want to say is that this is the, sorry about that. This is the Einstein, modified Einstein equation or FR equations of gravity. But the right-hand side, the stress energy, the matter term is 0, right? Because we are at this point trying to find the vacuum solution. So it's still, you can have any metric if you like, right? You can have any metric, non-singular metric, where the Kretschmann scalar is finite or 0. And you put it in Einstein equation, there will always be a stress energy tensor, in most cases anyway, which will satisfy that equation, right? So for any metric, you can almost always find it as a solution of Einstein equation, provided your stress energy tensor is funny or it's weird or something which is very unusual or unorthodox, right? We don't want that. We want it to be all vacuum solutions. So that's what makes it special, I guess. And in the end, if you do the Einstein equation in its full adapted to the situation, I keep saying Einstein equation, I mean this equation. So it's a modified Einstein equation with FR gravity. I guess you can call it FR equations of motion. You end up with two second order differential equations coupled around, which is this. I wouldn't go into the detail. I'm happy to answer questions. In our paper, we have a pretty descriptive, detailed appendix, couple of appendices which does all the steps and all that thing, but I'm happy to answer any questions regardless. So we have these two differential equations, and now since we demonstrated that you can indeed have a potential, and I'm not going to show that again right now because I've shown it a few times, that you can construct a potential which is non-singular at the origin and can go as a powered law. I showed that, well, let me show it once again. So if you take this potential, you can see here that short distance, it is indeed a set of power laws, okay, a polynomial, if you like. So since that has been constructed or demonstrated, we can always choose the deviations from flat space to be of this form, and you can calculate. So this slide kind of shows how this program works, okay? So with that, potential, again, I keep kind of interchanging the words potential and metric, but there's a precise dictionary between the two. So if you know one, you know the other, sort of. But in any case, if you know this metric, this r power n, excuse me, you can calculate the curvature scalar, which is of this form here. You can also on the side do the Kretschmann scalar, and as expected, it goes to 0 at r equals 0. So it is a non-singular space-time in the sense of curvature going to 0. The curvature scalar is going to 0. And solving the set of two differential equations that I showed in the previous slide, you can also get a solution for delta f, which is, to remind ourselves, capital F is the derivative of small f, and capital F is equal to 1 for Einstein gravity, so delta F is a deviation from that. Now the program of this, the essence of this program, of this way of looking at things, and we were not the first, there were others, and we have duly referred, of course, in our papers and things like that, but we adapted it to our case, is you eliminate small r, which is, so there are two f's and two r's, right? So small r is the radius vector, as usual. You eliminate small r between capital R and delta f, okay? And then you integrate. So when you eliminate small r, what do you get? You get delta f as a function of capital R, right? And then you integrate it to find f of r, what it is, okay, up to a constant. And that constant you can, from boundary conditions, this constant has to be 1, because for Einstein gravity we know it's 1, okay? So again, just to repeat, we write the metric, the non-singular metric, we calculate the curvature scalar, we calculate the deviations from the derivative of f of r gravity, we eliminate small r between the two, then we write delta capital F as a function of capital R, we integrate it to find capital F, we integrate it once again, and we integrate it to find what f of r is. And again, as we expected, the first term is Einstein, and the second term, so this is the term which governs the behavior of the non-singular potential in a covariant way. The C is a bit complicated, and it's all written here and that kind of thing. So essentially, for at least for the analytical part or the metric where it's non-singular and analytical, at least for that part, we have indeed found an explicit form of a covariant theory which would govern the dynamics of that for short distances. Any questions yet? All right. If not, I wouldn't delve too much into this, but right. But for the non-analytical potential, so this is, again, this goes to 0 at r goes to infinity, and space is flat, but this is the metric, and the potential is non-singular at the origin. For these two, you can find it's a little bit more difficult to find the analytical exact form of f of r, but you can write it implicitly, and I think I've drawn a graph there. So for the non-analytical form of the potential, you might have to do a numerical calculation to see. So here the point is, you see, even for that, the delta f is not 0, it's something there, which means there is a change. There is a change. So there's a non-trivial f of r theory which governs that potential, and you can at least numerically calculate that, and it's different from Einstein. So that was the point. Now, so what we have shown so far is that you can have a set of space-times or potentials in Newtonian language, which coincides with Newtonian or general relativistic at large distances. At short distances is non-singular, and for that you can have a precise field theory which is classical. You can also have field theory, classical field theory. Well, it's classical in both cases. What I mean is, you can have a classical field theory which is non-relativistic or Newtonian. You can also have a classical field theory in terms of FR gravity, which is indeed covariant. You can calculate the light cone structure. This is again standard, demonstration that's done for Royston-Nordstrom or Kerr, or even Schwarzschild black holes, or even cosmological spacetimes. So we take the metric that we have for the analytical potential, and I've chosen some value of n. I forget for the pictures, 5 or something like that. Anyway, you can define the tortoise coordinates. In this case, there are two. Oops. Sorry about that again. Something wrong with my. Yeah. So there are two, so-called horizons for this space-time instead of one for Schwarzschild. So the inner horizon kind of shows up at short distances, and again, the L is the length scale which determines all that. With the tortoise coordinates, you can construct the so-called Eddington-Finkelstein coordinates. I don't know if I wrote the name there, but in any case, where you can define the coordinates in this way. So light cone coordinates v and u, and from there you can write the ingoing and outgoing coordinates. So this is the picture basically, okay? So the two vertical lines are the two horizons. The straight lines, I should have said the straight slopey lines, the straight lines with the slope, they are, you can show from here, and you can actually clearly see from here, they're the ingoing light rays, and the curved lines are the outgoing null rays, and therefore these small circles, they coincide, well, they signify the light cones. Outside the outer horizon, the light cones are, as they should be, as you can see, on like very similar to what's at asymptopia. inside the horizon the light cones tip, and inside the inner horizon and tip back again. And here, essentially in this here, it's flat space, okay? So which means this is another way of saying that if you have the geodesics here, the geodesics will, when they come here, so here there's an issue here, but when they come here, it's basically flat space and the geodesics go on forever. Okay, so it is a geodesically complete space-time, and it's non-singular. I mean, it is non-singular because it is geodesically complete, but we did get a hunch that it would be non-singular because the Kretschmann scalar, everything was singular as non-singular as well. But this is like the demonstration in the space-time picture and in the spirit of let's say the Raychaudhuri equation and the singularity theorems. All right. So this is just again, I already talked about it a little bit. And just to emphasize once again that the potentials and the metric that we have, it's such that there's almost like a transition from the general relativistic or Newtonian regime to one which is non-Newtonian and non-general relativistic, but it's relativistic still. And so there's an attractive region, there's a repulsive region, there's a transition between the two, and the speed of transition, or how quickly the transition happens, that depends on that index or the number n that we. What about the effective coupling constants? Now, it's just an observation, and obviously work needs to be done, but I'll just take the observation anyway. For the FR gravity theory that we formulated, okay, for the FR gravity theory that we formulated, the coupling constant is no longer like Newton's constant, because that's the coupling constant R, and you can see from here as well that the effective coupling constant, which we call kappa bar, bar because of c bar anyway, that's g over c bar. C is not the speed of light, c is that constant which we had in an earlier slide, and you can put it here. And if you check the dimensions of that, the dimensions of this coupling constant for this new theory is whatever we write here. So mass power 4 divided by n minus 2 and things like that. And you can of course show that all of these go back to Newtonian or Einstein, like G for standard general relativity. But in any case, and if you have n equals 0, which is gr, as we know, the dimensions of the coupling constant, it is the wrong dimensions, right? It's 1 over mass square, which is length square, and that's one of the first and correct signs that why the theory, Einstein's gravity as a field theory, is not renormalizable, right? Because it has the wrong dimensions. On the other hand, if you take a very large n, which means a very quick transition region here, right? A very quick transition region, which is for a very large n, the dimension of the coupling constant almost or asymptotically goes to mass power 0, so dimensionless. There's no claims here, but just saying that, so in light of the fact that now that the coupling constant is correct in the sense it is favorable towards a renormalizable theory, it's worth examining. Note that when I say that the power, it becomes dimensionless, the power of mass is 0. This is exactly what happens for Yang-Mills theory as well, right? The fine structure constant, or the Yang-Mills coupling constant, or the QCD coupling constant, they're all dimensionless. So something like that interesting happens. It's certainly worth examining. And another interesting observation which we found is, again, for some reason, the small n number that small n, but large values of small n somehow, to me, intuitively sounds kind of a good thing. But intuition, I can't prove it. But large n seems to be coming back over and over again. As I said, for large n, the transition is very quick. The coupling constant becomes dimensionless, the gravitational coupling constant. And the FR theory of gravity for large n also is interesting, because for large n you can do a series Taylor expansion, and you can write it as 2 plus 2 over n. Okay, it's just a simple algebra from here. And if you write delta to be 2 over n, you see the model that you get here is practically a Starobinsky model of cosmology or of inflation, but with small deviation. Okay, and in fact for n going to infinity, the deviation is again really small. So Do I have about 6 or 7 minutes?
Yes, sure.
Okay, and maybe I can talk for another 2 or 3 minutes and then questions. Okay. So, so this is the main part of my talk. Okay, so the main part of my talk, and I'll summarize in a couple of minutes. But we are doing something else as well, and I won't go into too much of the details. This is again for those of you who and many of you may be aware, this is essentially the Starobinsky model of inflation. You can modify it by a little bit, and you do get, like, you can do a conformal transformation. You can get an effective scalar potential, which drives inflation. And these are some of the observables, which are the spectral index, as we know, the tensor to scalar ratio, running of the spectral index, and they can be written in terms of the slow roll parameters. And in this case, what we can do is we can rewrite everything in terms of our delta, which is, to remind ourselves, it is this index here. So our model is 2 plus delta. We can write it there, and we can actually invert and find what delta is in terms of the observable quantities, the scalar to tensor ratio, running of the spectral index, and all that. So the reds are, that's the color code I think I tried to make. The reds are the observables, and the black delta is what you need. And you can, for example, these are values I use, probably a year old, couple of year old. You can update it, once a year or whatever. But given the observed value, you see that there is a, long story short, but there's a small window here which is allowed, the small delta, well, small window for delta, which is allowed, okay? Delta positive, I mean, okay? And the window is small. It's from 0 to 0.03, and that's good because the smaller, the tighter a model is from, is made from observations, the better, for sure. And what's our n? It's roughly, it's 2 over delta, right? So at least from here, it looks like n is a couple of hundred or something like that, right? If we seriously take our model and we try to do calculation with it, which is fine by me, because I large n for some reason sounds right to me. You can do another plot, and again, I'm not going into details because I'll summarize. And here also you can see this is here, delta is sort of unrestricted, but it's certainly consistent with this graph here as well. So I think I should conclude. It's yeah. So let me summarize. So our aim was to find a singularity-free theory of classical gravity, because if the classical theory is singularity-free, even the compelling case of quantization kind of has to be revisited, right? Like there can still be a quantizable theory, a quantized theory of gravity that would be useful. Or maybe there isn't, because gravity is a different kind of force, right? It's not exactly the same as, it's quite different. We showed that there is a class, analytic, non-analytic class of potential, which does the job. Every time that we try to do that, a new scale emerges, which is physically satisfying, but it's also interesting. But it also puts the burden on theories to predict experiments, right? So in any case, I don't think you can avoid the emergence of this length scale. And under this length scale, gravity is repulsive, and the quickness of the transition region depends on the index n. Both the Newtonian theory and the FR theory of gravity is defined. I kind of loosely call it asymptotically free gravity, without being too technical about it, because it is like it reminds us of the asymptotic freedom in QCD, where the force go to zero as r goes to zero. It's very similar happening here, and as expected, but we showed rigorously again that the space-time is theoretically complete. Implications for quantum gravity. This is like a whole new set of problems that one can look at, and we are seriously looking at the implications of cosmology as well, in particular whether this could be a natural place or reason why the Starobinsky model is important or arises. So I'll stop there. I'm